Okay, so the recording started. Hi everyone. Before going through, I apologize whoever joined the YouTube live link just a couple of minutes back, and apparently it didn't work out because the way the slides were showing up in the screen were not optimal. So as a last resort, I just opened up a BlueJeans link so that we can quickly do it, and I can record it and I can share the recording later on the Piazza post. I again apologize for the YouTube live mess up. I have not done YouTube live often. Uh, I Let me just share my screen. Okay. Okay. Are you guys able to see my screen? Can anyone confirm if you guys are able to see my screen?
I can.
Okay, that's great. Thank you. Okay, let's go. Um, okay, so in this session, I will go through assignment 3 BaseNet, and we will be discussing first the assignment details, like what is this assignment is, like what are the important timelines that you need to be aware of, and then I will probably talk about some of the key concepts in this assignment. I will not go deeper into the concept because that is what you will probably be learning in the classroom or in the textbooks. I will though touch upon the topics that you are expected to know to solve this assignment, and then we will go through the GitHub repository and we will see what each component and what each problem is, and then we'll talk about the scoring mechanism. What are the scores for each section? And then we will talk about testing, like can you test locally and how the Gradescope test is done. And then finally, I will close up with some suggestions that I would like to give you guys. So the first thing in the assignment detail is that the assignment is released on 27th of September, Sunday midnight. And I hope that you guys have already started working on this assignment. And The end date is 10th of October, so be sure to submit it before the deadline. And if you need any accommodations or if you need any extension after this deadline, then please reach out to head TAs as soon as possible. Uh, the material covered in this is the module 5 and 6 and the probability chapter in the textbook. So yeah, let me just touch upon some of the brief concepts that will be covered and that will be helpful for you to uh, go deeper into these topics using which you can solve this whole assignment. So the first thing is the BaseNet. So as you know that BaseNet is basically a graphical representation of your random variables where each node is represented as a random variable, and it's basically a set of directed links notifying a cause effect or a parent child relationship. So for example, in this figure of this example that I've taken from the textbook, if a burglary has happened, then an alarm could ring in the apartment. Similarly, if an earthquake has happened, then an alarm can ring as well in the apartment. So it's a parent-child relationship. At the same time, it's a cause-effect relationship. The burglary can cause an alarm to ring. Similarly, an earthquake can cause an alarm to ring. And each node has a conditional probability distribution where the probability of particular node is conditioned on the parent's xi. So the probability that alarm will ring it dependent whether the burglary has happened or whether an earthquake has happened. And we call these an evidence variable. So if we have to calculate the probability of xi given the parents of xi, this parents of xi is basically an evidence variable for this particular case. Some of the definitions that I think you must be aware of is like the prior probability, posterior probability, marginal probability, and conditional probability that you would have to calculate in this assignment. Prior probability is basically the probability that an event will happen before you have taken any evidence into account. So any new probability that you're calculating, it's your prior probability. The posterior probability is that the probability of an event that has happened after all the evidence has been observed or collected. So in the previous case, if I talk about it, basically means the probability that an alarm has ring given the burglary has happened or given an earthquake has happened. So these are the evidences that you have. So if I have to combine both prior and posterior, the posterior probability is basically a prior probability plus your new evidence, which is also known as the likelihood function. And then marginal probability is basically the probability of one variable irrespective of the outcomes of the other variables. For example, what is the probability, if I go in the previous example, what is the marginal probability that the person John calls? So the marginal probability of John calls mean that considering all the scenarios, considering burglary has happened, alarm has rang, John has called. Considering earthquake has happened, alarm has rang, John calls. So you have to consider irrespective of whatever the values the other evidence variable or other variables hold, what is the probability that a John calls? That's the marginal probability that you have to calculate. Then the second part of the assignment will majorly deal with Monte Carlo simulation. Which is basically a method of estimating the value of an unknown quantity using the principles of inferential statistics. Now, what is an inferential statistics? It's basically mean that you have given a population, and this population is also known as the universe. And let me take an example to explain this. If you talk about an example of a game, let's say solitaire game that you might guys have played in the old computer, like the solitaire game of the cards. So if you talk about the solitaire game, the population in that game is basically all the possible sets of the game that can be played. So it's an infinite set of for the solitaire game. There could be infinite ways that this game can be played. And the sample is basically you basically pick up a proper subset of from this whole universe. So if for the sake of this example, if we say let's say if we have 100,000 universe of 100,000 examples, you take only 10,000 samples from this subset. So the key fact or the key idea here is that a random sample that basically you have picked, it tends to exhibit the same properties as the whole universe or as the population from which it is drawn. And that is the idea that is being used in both the algorithm, the Emmet sampling, and the Gibbs sampling that you will be implementing in this assignment. And Monte Carlo Markov chain is basically the model where describing the sequence of all possible events where the probability of each event depends only on the state achieved on the previous event. So what basically this means is basically you pick one random variable, you pick a random variable randomly at once, and then you set a value, then you move to the next timestamp. So if you go through the let me quickly open the link for this assignment. So, okay. Yeah, so in this example for the resources that have been given to you is the Gibbs sampling. So in this particular example here, that which is given is a base net of cloudy, if it's cloudy, whether the sprinkler is turned on or whether a rain has happened. And if a rain has happened, whether the grass will wet or if the sprinkler was on, the grass is wet. So here, for the sake of this inference problem where you want to estimate what is the probability that the rain has occurred given the sprinkler and wet grass are true. So these two green nodes here are the evidence variable which are given to you. You are not given if the weather was cloudy or not. And now you have to infer from this information that what is the probability that it is going to rain. So you basically, what you do is basically you initialize a random sample. The meaning by the random sample is basically you set the value of each of these variables which you don't know randomly. You say, okay, let's begin with saying that rain is true, cloudy is also true, and so your initial sample will become rain true, cloudy true, and sprinkler true, and wet grass true, which is given to you in this inference problem. So you start with the with some initial point, and then you basically do an iterations, and you update the values of the non-evidence variable that you have to calculate. And how do you calculate it? You pick randomly one of the non-evidence variable here. Let's say you pick rain. If you pick the rain, then you sample basically rain. You calculate basically this conditional probability, that the probability that the rain will happen given the cloudy is true in the first iteration for t equals to 1, where the value will be at 0, and the value at 0 you picked as true. So given the cloudy true, sprinkler true, wet grass is true, what is the probability that the rain will happen? So that is the first sample that you will calculate. And this probability value you will set at this point t equals to 1. The probability of the rain, the sample for this rain will be the value at t that you calculate in this step 1. And the cloudy value will be t minus 1. If you pick cloudy, vice versa, you will do the same for the cloudy, where you will try to calculate the conditional probability of cloudy given what was the value of rain at t minus 1 iteration, and the rest of the evidence variable is given to you. And you will repeat it until you reach a stage of convergence where where the probability that you're calculating doesn't differ much. So you are basically repetitively you're getting the same probability. So that means you now have enough samples, or you have done enough sampling to say or to infer that okay, this is as a whole I could infer that this is the true probability that it will rain given the sprinkler is on and the grass is wet. So that is the idea here. Image sampling, it's basically to determine the posterior probability without knowing the normalizing constant. You sample basically all the variables at one time, which basically means that you have all the non-evidence variable. You basically pick all these non-evidence variable at once. Evidence variable won't change because the values for them will be given to you. You need to calculate the non-evidence variable, and the way to do is you pick all of these non-evidence variable in one go. And so in one go you will have a full sample. And now what do you do with the sample? You can either accept it or you can either reject it. The way you accept it or reject it is using the acceptance ratio, which you will read in the textbook. Which is basically a pseudo-random method where the likelihood of acceptance will be higher if your ratio is higher. And if you accept the sample, you basically return this sample that you just randomly picked. And if you reject the sample, then you basically do not return this sample that you have picked. Instead, you will pick the previous sample, or you return the original input list in form of a tuple in this assignment. Gibbs sampling. Gibbs sampling is basically a special case of image sampling. It is basically applicable when the joint distribution is not known explicitly or is difficult to sample directly. But the condition probability of each the variable is known to you, or if it is easier to sample, which is true in our assignment, where you will have access to the conditional probabilities, and using those conditional probabilities or the match table or the game table, you will be able to implement this Gibbs sampling. The major difference in Gibbs sampling and image sampling that you have to know is that in Gibbs sampling, you are sampling one non-evidence variable at a time. So at one time, you will only sample one variable and you will fix rest of the variable as same. But in the image sampling, you are picking all the non-evidence variable at once. Okay, so these are the basically important things that you need to read about. Go through the resources. So let me open this link, GitHub link. Okay, quickly go through this. Yeah. So this is the assignment repo here. You all should have access to this by now. The resources is, like it said, you have Canvas videos and you have textbook chapter 13 and 14 to read. Some of the resources that are mentioned here are very important. Please go through them and read all of them. They are very helpful. They will be helpful in implementing all of these algorithms. And if there are some couple of videos in YouTube also, which I believe from in the last semester, which helped students a lot. I do not remember the link for them. I think it should be easy to search them on the YouTube. If you are not able to find those videos, just please ping me. I will try to find those videos for you guys, and I can share them in the Piazza. Uh, so. In this assignment repo, the first part is setup. I think the important thing to notice here is that if you have done assignment 0, then you should be good. The thing is to notice that we are using Python 3. So if you're using Python 2, you will face problem because the libraries that are being used here are Python 3 based libraries. So that is the thing that you need to take care of. Rest of the things here, I believe the same as you're doing in the previous assignments. Submission. This is very important. So there is a total submission limit of 5 on the grade score for the assignment, which means that you can submit a maximum of 5 times during the duration of the assignment. It doesn't matter if you submit the part 1, if you're submitting part 2. Overall, you will have 5 chances to submit this to grade score. The reason to do this is basically the exercises or the assignment or the parts of this assignment are such that you can brute force your solution. If we give you infinite number of submissions in the grade scope, you can easily brute force your solution and can get a full score. So that is one of the reasons that we wanted to limit the number of submissions so you can learn at the same time figure out on your own if you are doing things right or wrong. So uh, one caveat or one catch here is that if your submission, let's say timeout in the grade scope, that submission is not count. So for some reason, let's say in last part of the sampling, if you are running it and let's say the grade scope timed out, then you don't have to worry about it. So you can submit it again. So timeout is not considered as a submission. Restrictions, please do not use these 3 libraries. If you use these 3 libraries, then the whole point of learning or whole point of implementing these algorithms will be in vain. So please do not use them. Part 1 is basically the Bayesian network tutorial, where basically you have given a scenario and you have to implement a Bayesian network for this scenario. And this scenario is basically consists of a nuclear power plant in which an alarm is supposed to ring, where the gauge reading exceeds a fixed threshold, and based on the reading reading on the temperature, you basically say that there's some problem in the nuclear power plant or not. The catch here is basically is that the two things, the gauge which reads the temperature can be faulty. That means it can sometimes read wrong temperature. Second catch is basically alarm is also sometimes faulty. Sometimes alarm can ring and sometimes it cannot ring. So alarm can fail and the gauge can also fail. Okay, and with the chance of failing greater than when the temperature is high. Now read through, I would suggest read through all these statements here, which are there to help you decide what is the probability of each of these and use these naming attributes. Please stick to the syntax here. The reason I'm saying is that because in the Bayes net, when you call the function here, when you add the alarm here, so the node will be named alarm. Many times I have seen in the previous assignment also where students basically have some syntax mistake where they misspell or have an extra space here, and when they add, something breaks. So make sure that when you are naming these, you name it properly, and and the naming should be consistent throughout your implementation. So if there's a gap between faulty gauge when you're adding here and when you are adding the edge, so make sure you use the same name. So that way you won't face any problem with that. The way to add the node is basically you can call the function method add node. The way to add an edge, you can call a method called edge, where there is an edge that goes from temperature to alarm. Now The way to go about this assignment, which I have seen many people have asked in the Piazza also, like, and people face difficulty in implementing is like how to test it and all. The key idea here is that get a paper and pen, read through each statement, try to draw a base net for this. Okay, just like I was talking about the burglary example to you guys, similarly draw a base net for this particular scenario. Once you have drawn the base net where you have the random variables in the nodes and you have the CPD tables for each of these node, then adding these values, solving this first part is just a matter of syntax. These methods here won't trouble because the implementation is basically will take you 5 minutes if you have properly solved this, if you have properly implemented this basenet in the copy in a paper. So please do that before directly jumping and before directly adding into the code. 1B, the setting of the probabilities, basically there you will basically the condition probability distribution that you have calculated for each of the nodes, you will fill it here. So if I have to refer it in my example previous year, what I'm talking about is these probability distribution. So in your basenet for each node you will calculate a CPD table, right, like this, and these then you will have to fill. And this is what you will do in this setting of the probability function. And the way to do is been given you with this by calling this particular class here. And you can read about the details of this class, like what each points here means here, and how to put the values in here. And you can refer this the library here, the link provided here. One of the thing to note here is that the index 0 represent false and the index 1 represent true. So make sure when you are returning, I know it could be a little bit inconvenient while you're implementing, because when you draw in the copy, you always have in your mind, true first and the false then. But when you are implementing here, this first 0.3 here means false. The probability that A will be false is 0.3. The probability that A will be true is 0.7. And let's say, suppose if you're implementing like this here, it means that the probability that A is false, the probability of false is 0.15, then the probability true is 0.25, probability false is 0.85, probability true is 0.75, and this whole is also a probability of false. So false always comes before the true here, and in the implementation in the library. This is just the way it is. So just make sure when you're implementing so that you won't face any issue there. Okay, so I think this is then straightforward. Implementing these things, and yeah, and the evidence that you will call once you have an evidence value, you can just add them in the evidence parameter here, what evidence you are giving here. And I think, and then at the end, once you calculate all the CPDs, you can add them to your basenet, and that's it. And then you can test it locally with the test function here. Part 1C is basically probability calculation, that is performing the inference there where you calculate the marginal probability that the alarm will sound, the marginal probability that the gauge shows it's hot, and finally the probability that the temperature is actually hot given the alarm sounds and the alarm and the gauge are both working. So some inferential calculations that you have to do. For this also, please solve it on copy, because not all the test cases are covered here. Okay, there are very few test cases that are covered when you test this locally. So when you submit it to Gradescope, there are further test cases that are run there to test the distributions that you are doing. So if you have solved this whole questions in copy and pen, if you have tried to calculate this marginal probability alarm sounds in the copy pen, then it's very easy for you to verify if your method is working or not. If the values matches, then it's very high likely that your implementation is correct and you will get a full score on that. You can use the variable elimination class here for this, specifically to get the marginal probability, and this is just the syntax, and this is all you have to use. So let's say, for example, you have to calculate the marginal probability of alarm sounds. You do it in the copy or pen, You solve it, you get a value, let's say 0.7 or something. And then you just have to, in the code, you have to just call this variable elimination, pass your base net, and in the variables, you just pass the alarm value, join false, and you get the values. And then see what values you are getting in here. You should be getting the same value that you calculated in the pen. That's it. These three lines is the everything that you have to do it for each of these things here. Okay. Um, The note here is that the marginal probability and the conditional probability returns two probability, false and true case. You must index into the correct position in probability to obtain the particular probability value that you're looking for. Yeah, that's, I think, understood. Um, okay, so this here means the same thing that I was talking about. For inference, you can pick any of the examples above and you try to calculate it from hand and run this inference code and then see if you get the same value or not. And you can just double check this thing. Part two is basically sampling. It's basically here you have given a different scenario. The first scenario is based on a nuclear power plant. The second scenario is based on the game between three teams A, B, and C. And the first part is basically, so there are three parts. I think there are three parts. I think there are, so the majority of the part is basically first you build a network the same way that you do in the first part, based on reading these statement, based on reading all the information, what is the match happened, and between whom, and what are the skill levels of each of them. You basically create a base net, exactly like you have to do it in copy and pin. And once you have created a base net, you will implement the same base net that you have drawn in the copy in the basically in the first 2A part where you build the network. And these definitions are, I think, self-explanatory. But let me know if you have any confusion in understanding any of these variables and what these denotes here. Part 2B is basically calculating the posterior distribution for the third match. So you have given here the statement that suppose that you know the outcome of the two of the three games. A beats B and A draws with C. So this is the evidence that that has been given to you, that A versus B is given to you and A versus C is also given to you as an evidence here. Now you have to calculate the posterior distribution for the outcome of B versus C match in this second statement here. And you have to use the same evidence in all the parts afterwards. When you're implementing Gibbs sampling, when you're implementing MH sampling, you need to take into account the same evidence there. So you won't touch this evidence there. You will basically sample the rest of the non-evidence variable that you have, which is A, B, C, and I think A versus, I think B versus C. Yeah. So you will sample them instead of these two. You can use the variable elimination provided to perform the inference again here, and you can check your posterior distribution that you are getting here. I think the hints here in yeah, the same thing that I talked about in the slides is that in both MH sampling and Gibbs sampling, you will need to access the CPD values of the matches bit of A, B, and versus A, B, and which you can get using these methods here. You can use it. And one thing is that while performing sampling, you need to have an initial sample by sampling uniformly at random outcome. So if you have given an initial sample, it's well and good. If you have not given an initial sample, you can initialize it to something that you would want it to be. Okay, you are free to use random.random and random.choice or any other random library that you want to use the random number that the Python provides. In order to count the sample states later on, you will want to make sure that the sample that you return is hashable, meaning that you can initially add the sample into a list, into a Python list, and then you can basically return it as a tuple. So you just have to call tuple and pass your list here, and then it basically returns as a tuple. And part 2C, I talked about it. Implement the Gibbs sampling. Given the evidence, these two evidence, A beats B and A draws C, you need to implement a Gibbs sampling where you will randomly pick the non-evidence variable. In Gibbs sampling, you will pick one random variable at a time, excuse me. And in the image sampling, you will pick all the random variable at all at once. The slide deck here provides a nice introduction. Please go through it. And I said, feel free to use YouTube or Google to learn more about these algorithms, how these works. And yeah, part 2E is comparing sampling method. Now, so in here in first and two, you are not basically implementing the convergence here. You are not basically implementing, you are just implementing one iteration of the GIF sampling and one iteration of the image sampling. Here in this 2E part, you have to run both GIF sampling and Metropolis Hastings sampling until it converges. So here you basically have to run it in a number of iterations. So you have three hyperparameters here, which basically you can tweak. The first is number of iteration that you want to run. Let's say 100 iteration. So let's say for 100 iterations, your GIF sampling converges, meaning after 100 samples, after 100 iteration, you see there is no change in the probability. And if the change is there, the change is basically called as delta. And you decide what delta it is. So you say, let's say I'm getting in the 100th iteration my probability at 0.0001, and in the 101 iteration you are getting a probability of 100 of 0.0002. So there is a difference of 0.0001. So you need to decide that what is the delta you want to choose. When do you say your algorithm converges? So basically, you have to tweak these two parameters: the number of iteration, the delta here. The third is the burnout period. So the reason to use the burnout period, and it is mentioned here also in the FAQs. If we go to the FAQs, and it is mentioned here is that what is burn-in period and why it is useful. The practice here is that you want to throw away some of the iteration at the beginning because you basically want to enter into a high probability region. So if you think about in terms of graph, when you are running these algorithms, you might sometimes not even reach the maxima in the peak where basically you would want where the whole the higher density of probability distribution is there. So you might stuck in the lower density region in that graph. So you might want to experiment with this burnout period. So initially, just for some period of time, you don't consider anything. So after some period of time, you will say, okay, now my algorithm is learning something. My algorithm is basically trying to converge or trying to understand this distribution. So these three parameters you have to experiment. Okay, so so what do? You converge for both this algorithm using these three tweaks, and then you implement this in compare sampling method. And finally, in the sampling question, you basically have to see which algorithm is running faster. So let's say your GIF sampling runs for 100 iterations with some value of n burnout period and delta. It run 100 sample and 100 iteration and it converges. For image sampling, let's say it takes 200 iterations to converge with some value of n delta or burnout period. Then that means your GIF sampling is efficient because you don't have to, you just exactly run half the iteration that the image sampling have to run in order for the convergence. So that is the factor basically. By what factor your algorithm is efficient. So here your GIF sampling is effective than your image sampling by a factor of 2 because your image sampling is taking 200 iterations and your GIF sampling is taking 100 iterations only. So that you have to fill in this. And finally, you have to return your name and the part 2F. That is it from the whole project point of view. The scoring is basically the first designing the nuclear power plant Bayesian network is 10 points. Conditional probability distribution setting the CPD values is 15 points. I think you get the full points. I'm not sure about the partial marking is there or not, but I believe if you implement correctly, you get the full marks there. And then for the 1C, performing inference is 10 points. Building the network for the second scenario, the match between A and B is 10 points, and calculating the posterior probability for the outcome of the B versus C match is 5 points. Implementing Gibbs 15, image sampling is 15, and finally converging these two algorithms and comparing these two is basically 19 points, and then at the end you return your name. So that's the scoring part. Testing, you can locally test your implementations using the probability test.py file. Feel free to open it and check what each of these test cases are doing here. So you can open these and you can see what each of these are doing here. You can see that the part one is basically checking that you have proper number of nodes and edges, and the second part is basically testing all the nodes in the power plant network have a proper probability distribution. That is, you have calculated the CPD values correctly, and that the node names you have implemented is correctly here. So you can feel free to take a look at these, and locally if you want to modify this and if you want to modify and add some of your own test cases, feel free to do so. Not all the test cases here are covered. Like you see, only part 2B till day we have the test cases. After that, there's no test cases here. The test cases are implemented in the Gradescope. So Gradescope, there are series of unit test cases that are there, which are not in the local test for the scoring matter, to see that you have implemented it properly. Basically, yeah, what Gradescope checks is how well you have set up your network, meaning that the nodes and the edges are set it up properly. It checks basically you get the probabilities right within the margin. There is a margin. If you get some, there's some margin of error is allowed. I'm not sure how much it is, but I can check it for you guys. And so these probabilities basically the CPD values that you are calculating, and yep, you only get 5 chances to submit it. My final suggestion for this whole assignment is please start early. Read the book, watch the video lectures, Google these algorithms, learn about this algorithm. You can see some videos also from MIT, and you can see some videos from different people, and try to understand what is this algorithm is about, how it is done. Please read the FAQs, and most of the problem that you will see will be in FAQs most of the time, because these are the questions that has been asked multiple times in the previous semester also. So please, asking before any question, please go through the FAQs and see if that is answered already there. Fourth point, read the resources attached to the repo. And fifth point, yeah, solve the questions with pen and paper first for all the problems until you reach to the Gibbs sampling, where you basically have to implement the Gibbs sampling. So until you reach the sampling, where you have to define the base net, where you have to calculate the probabilities, the tables, do it by hand. That is the most effective way to succeed in this assignment. I think, yeah, that's pretty much it from covering all these things. I can take the questions now. There was a question that, can you please explain the conditional probability? So think of the conditional probability is basically given an event has occurred, what is the probability that a new event will be occurring? So if I have to give an example of the same here, let me share my screen again. Let me stop the recording first.